Good morning, everyone. So it's always a bit daunting coming after Aaron because he's quite eloquent. But today, I will also be fairly informal. We're talking about sort of a project that I've just been fiddling with. It's not even in a state where I can put it on GitHub. I'm just like fiddling with things and ideas and have pieces of APL scattered about. So I just kind of want to take you down the rabbit hole with me on where my thoughts have gone and see where that takes us. So today's talk about formal proofs. So formal proofs in math. The background is, so the what and the why of formal proofs. When you think of formal mathematics, you think of white papers, publications in mathematical journals. But in formal verification, those are considered informal proofs. For the most part, the history of math has been people writing letters to each other, publishing papers, and the verification of proofs has been human eyeballs and human brains. And it's actually fairly common to have errors in published proofs of math. Even Fermat's last theorem, Wiles' paper that sort of closed that loop. There was a fatal error in it. But then, interestingly, these errors tend to be, you can work around them in some way. So it actually works out. But you kind of want to know, in math, you kind of want to know if you're going to publish something that it's solid, it's airtight. There are certain instances of proofs that have been put out, and people relied on assumed or just trusted that proof was solid, and then for 30 years built results on it, and then it turned out that was incorrect, and then you have to go back and unwind a lot of things. So formal verification sort of operates in this arena. Let's make math more solid. So formal proofs kind of just look like programming languages. Asher here is kind of looking at these, and we've had some discussions. But there's how many in here have actually looked at any formal verification systems before? We have 1, 2, 3. So we have a scattering of a few people here. And at their base, they're kind of rely on this analogy that can be made between programming languages and proofs. And the fancy term is this Curried-Howard correspondence. These two famous mathematicians. Maybe you've heard of like function currying and something. That's the same curry. And on the one side, if you have formal proofs, you would have something like natural deduction, which is what you think of whenever you're doing proofs, where you just start out with some things that you know, you use your rules of logic to naturally deduce a conclusion. And there's a way that you can transform like the formal way of you write this down into a kind of typed lambda calculus, which is a model of computation, a very stripped down programming language of sorts. And then logic programming languages and sort of some kinds of, especially like early logic programming languages, actually would take type lambda calculus and transform that into something, try and make it more usable per se. So there's actually like work that has been to make formal proofs in usable programming languages. And we see this today in some of them. Let's see if I have examples here. Yeah, so the history of formal verification systems actually goes back to 1973 or even before this, but like Mizar is a system that is still around where you can submit formal proof. There will be a peer review process. It'll be formally verified, peer reviewed, see how it's written, and then if it all checks out, it'll be published in a particular journal. And then we go through some systems. Isabelle. Some of you are probably familiar with Coq. That's a fairly widely used system. But then some of the other interesting ones like Agda and Idris here are aimed at just everyday quote unquote everyday programmers. They have type systems that are stronger than Haskell, like dependent type systems, but they have a lot of features. They have standard I/O and stuff, so it's not just for math proofs. But you have people on both sides of the aisle kind of doing this. Lean, which Asher is looking at and is quite enthusiastic about these days, is being used by professional mathematicians, and it also tries to be a general programming language, but we have current research level mathematics being done in this language. And then the one that I want to talk about today is Metamath, which has this property that it makes it's very simple language, very stripped down, so it makes it easy to verify. All right, and so the kinds of problems that these languages are targeting range all over the place, from simple things like Pythagorean theorem, where you can write that down, to Fermat's last theorem and research level problems. And kind of in the back of your head, I want you to be thinking of we have a lot of APLers here and not like type theoretic people, but if you're familiar with like any of strongly typed languages, if you've played with Haskell or anything in the back of your mind, I want you to kind of think a little bit about what it looks like to write down type signatures and do type inference and something that can give somewhat of a reasonable intuition for what it's like to write proofs. All right, so just a quick overview of just to get us all on the same page of how we normally think of proving something. So we're going to prove that we're doing groundbreaking work here, proving 2 + 2 = 4. But normally you would start with something like, okay, we know 2 + 2 = 2 + 2, just from like identity, right? So then we need to start, but you need to be careful, right? We need to make sure that whenever we're doing proofs, we kind of just want to do string replacement. Like to build a simple foundation for the kind of rules and the kind of machinery we're using to build a proof, we want to make that as small and as parsimonious as possible so that we can trust the process itself. If we have a big, giant, complex program or a big, complex machinery to prove some of our results, then we're implicitly trusting that there's no bugs in that machinery, right? It's like a big program, it could have bugs in it. So the machinery we're using is almost, isn't quite there, but it's almost just string replacement, right? So we know that 2 + 2 = 2 + 2 because just identity. Then if we know that 2 = 1 + 1, in the right-hand 2 there, we can just replace it, right? In the parentheses, I'm playing fast and loose here with it a little bit, but we need to put those in. And then from knowing our associative law, we know this. So in x, y, and z, we can, if we have integers, then we know that we can swap around parentheses with addition, and that's okay. And so if we know that these numbers here are all integers, and we have enough hypotheses here, we can use this step and go to here and switch our order of association. And then we have this linear flow through until we get to the end of our proof here. So for each step, we have a justification or a set of justifications that allow us to make this particular string replacement. And then normally, and this is how we would normally think of it, you just do this. Like if you've done proofs in geometry, it's sort of like this linear flow. We just go down one at a time. And if you're going to do this in a computer, and a lot of formal verification systems these days do have a linear reduction process where you start out with your premises and then you end up with your conclusion. But if we're trying to target like doing this in parallel. And so how does that arise? So let's do this again, but in a slightly different way. So as you can see, there's a tree structure here. Tree structure here. So we start out with with the conclusion up at the top. So that's the root node. And then we have a bunch of premises that we have down here, like 2 = 1 + 1. 1 is a complex number, and it's a number. It's a number. This is what this is trying to say. We have 1, 1, and 2 are numbers. 3 = 2 + 1 by definition. That's how we can define 3. We have some of these definitions. And then the node that these premises come into, we can combine them into a statement, right, like this. And I didn't write down the justifications for this, but this would be the associative law that we had. So this one would combine by moving parentheses, we can, as long as we have those come in, then we have this, right? And then the same thing, this node and these other 2 nodes here will feed in to give this node. And so if we were going to verify this, we could just start at the bottom of the tree, at all of those premises, and then move up one level. So we could prove this and this at the same time. Whereas in our past proof here, everything was linear. So in order to get here at any place, we had to go through this, right? So this is just you don't have to follow the details exactly, but just to show that, and proofs naturally have this tree structure to them. And in general, if you're writing something, there will be like sub-lemmas inside of a proof. And that's what this looks like. That's what these interior nodes correspond to, are sub-little lemmas that you end up using and reducing down to your goal result up at the top. Okay, and so Metamath. In Metamath, this is kind of like what a proof looks like. And you can see, just to like preempt this here, you can see there's this sort of tree, this nested structure. And that's encoding the tree structure of the proof. Even though Metamath doesn't do its actual verification in parallel leveraging this. But it's sort of a recapitulation of this last. We're also proving 2 + 2 = 4 here. And the tree that I wrote down is the same thing here. We're seeing the exact same thing. But what we didn't have on the other slide are the justifications. So we have on each of those nodes on the right-hand side on this sort of jagged column here, on the right-hand side of an equals is a name of a theorem or a hypothesis that this line corresponds to. On the left-hand side of the equals is the justification that lets us unify into that. All right, so this is just to give you an idea of what the target language that we're using. It's particularly simple because we just have a few proof objects, a few axiom objects, and then we can use those to bind the hypotheses with internal proof nodes here. Okay, and so how do we treeify? So okay, let me back up a little bit. In Metamath, the proof itself, when you write it down, modulo other tools that can help you, you have this target, or you start out with a target that you're trying to prove, like this 2 + 2 = 4. And then you come on with some assumptions in the beginning, and then you have a whole database of lemmas and theorems that you can use. And the proof, starts out with, it's just like a stack-based language where you put anything that you have, any hypotheses you have assumed or other things you have proved previously in the database, you can put those things on the stack. And then to put a new thing on the stack, if it requires other hypotheses, it has to pop those off the stack. And then if it can actually pop those off and match, it's sort of like a function call, right? So you have something on the stack, it pops a few things on the stack, puts it into its arguments. If those arguments fit with the type that the function that you're trying to call, this theorem that you're trying to call, matches, then it'll put its result on the stack. So it's just a stack-based language. But if you're going to prove, then it's a linear scan through these list of proof tokens, these labels for each of them. And what we want to do is turn that representation into a tree representation so we can leverage like all the stuff that we learned whenever we read Asher's tree manipulation stuff last night, right? So this is a very naive algorithm to do this. We start off with, if we have at each label in the proof, we know how many arguments it takes, how many hypotheses it needs in order to unify. And this first line here is able to turn that into a stack depth vector, and then we can take that stack depth vector and turn it into, what was I doing? Yeah, we turn it into a parent vector representation with these two lines. But this is a quadratic algorithm, and it's not so great. I'm trying to figure out like a better way to do this. But what this allows you to do is, in the standard way of reading a Metamath Metamath database, you'll ingest this big giant text file. It'll load it into memory, so it does some pre-processing step. And so this is what I'm thinking of as like a pre-processing step. I'll load this into memory, generate a parent vector, and then we can do the verification after that step. Yeah, I think I have some ideas to actually linearize it, or parallelize this, and we could have the entire flow, after parsing, the entire flow be parallel and just beat the pants off of some of these other verifications. So, I think I already went through this. So data parallel proving, just to recap a little bit, this is probably easier to see. You can start off with a bunch of things that you know or things that you assume at the bottom, and then combine them to build the next layer of nodes, and it would just propagate up the depth of the proof tree instead of going down like you would normally do in traverse to a tree traversal. Okie dokie, we're going deeper down the rabbit hole like this. And so using this technique, Metamath, it has a database of about 250,000 proofs, maybe a little less than that. And it takes, on my system, it takes about 5 seconds to prove the entire database. Now compare this is blazingly fast compared to other systems. Like Mizar, if you're going to try to prove all of their proofs, it takes days or weeks. On Lean, they have the newest version of Lean, I think is 4. I don't know if they have anything after that. But the main database that is used is called Mathlib, and it takes hours on a very fast machine, sometimes even more than a day if it's just like a normal laptop or something. So even Metamath, like just a few seconds, is just ridiculously fast. But if you want to put this in like sort of a loop where the human's in the loop, where you're wanting to have like a linter or something, for example, for writing proofs, having every time you typed something, having to wait 3 seconds or 5 seconds or even 1 second for feedback is just way too much. So my goal here is I'd like to push this under like the 200 millisecond threshold, where you could be writing proofs dynamically, and every time you enter a character on the keyboard, it will verify the entire database and make sure that your proof that you're working on is reasonable. And the reason that you could do this if you were able to isolate one individual proof out and then just assume everything else was proved. But if you want to if you're jumping around between theorems and lemmas and you're trying to manipulate a large structure and you're trying to design a proof, then you need to be able to have this ability to verify a whole swath of things across the database, because you can have these interdependencies between. And so being able to parallelize this, right now we're getting about not quite where I want it to be, but we're getting under a second after we've done this ingestion step. So we're faster than Metamath already, but I think we can do better. All right, and so is this the bottom of the rabbit hole? Definitely not. I mean, I'm really curious if we could throw this at CodeFunds, if we did, and see if we could. I don't know how I don't know how this would parallelize on the GPU and how well it would work, but it could be interesting if we could get this to some blazingly fast verification times. So in the formal verification community, there are some people that have research projects that are trying to do this tree data parallel verification process, but they have architected entire large systems in Rust or something in order to achieve that result, and they have to change the language significantly so that you're putting all kinds of type information and extra layers of complication on the proof writing language itself to enable them to make this inference, right? But we can just take a very naive, very simple language that is out there and being used in the wild and make this blazingly fast. That can make waves in this community, right? So I think that there's a reasonable story here that using some of these tree manipulation techniques, there are problems that APL can address in a way that's more compelling and less effort, and it allows us to connect with other, not even just academics, but other technical communities that are outside of APL and don't even have APL on their radar. So yeah, what did we see? I mean, recap. So normally we think of proofs as this linear stepwise process, but we saw that there's actually a lot of nesting structure of lemmas inside of them, and we can leverage that to start from the bottom of the things that we assume are true or know are true, and then prove prove several theorems in parallel. And we can take that and use that as a communication tool to some of these other domains that have tree structures nested in their technical problems that they're dealing with, and show that, hey, APL is really good at this. What I don't have a strong story for is why should we as APLers care to bring the outside world into us, but I think as a communication tool and a way to grapple with some of these other problems, this is a really interesting test case because it's simple. So thank you very much for listening to going down this rabbit hole with me. We went way down like that.